Okay, so this time we're going to apply entropy to some kind of extremal problem in the hypercube. I think we talked about, did we talk about the I think it came up at some point in the course already, but let's talk about it again. So n-dimensional hypercube, Qn, is the graph with vertex set. Oh yeah, this came up maybe when we proved a bound on the extremal number of the three-dimensional cube, right? Anyway, the vertex set 0, 1 to the n, where if I've got u, v in the vertex set, so uv is an edge of Qn if and only if u and v differ on a unique coordinate. So for example, I mean, you should think of these vertices as like binary strings. And two strings are adjacent if they only have one difference between them, right? So yeah, so this would be Q1, Q2, Q3. Looks something like that, right? Okay, so here's the problem we're going to consider. So for n at least 1, and let's say k is between 1 and 2 to the n. What I want to do is find out like or to get an upper bound on the number of edges that can be contained in a set of vertices of size k. So what is the maximum? So E of A is just like the number of edges contained within A among all subsets A of the vertex set of Qn. In other words, 0, 1 to the n, with cardinality equal to k. So yeah, you've got a fixed kind of budget in terms of number of vertices you're allowed to pick, right? You can pick k vertices, and I want to enclose as many edges as possible within those k vertices. So this is kind of like I mean, in other areas of math, like maybe geometry or things like that, you might call this is kind of like an isopermetric problem. What do I mean by isopermetric problem? Like you could have, I mean, if suppose I have a string of length 1, and I want to like enclose a region in the plane, with a fixed perimeter. Isopermetric means, right, like a fixed parameter, and you want to enclose the biggest area, you'd probably take a circle, right? So that's kind of like this is kind of like a similar type of problem, except we've got a fixed number of vertices. So that's kind of like the fixed perimeter. And instead of like maximizing the area of the shape that you make, you're maximizing, the number of edges, right? Questions about that? Okay. So it's not really clear what the right strategy is for this. But if k is a power of 2, there is kind of a natural construction. So suppose k has the form 2 to the t for some t at least 0. Then like one construction so for example, like if we're in the three-dimensional cube and I say pick 4 points to maximize the number of edges, one nice thing you can do is like pick a face of the cube, right? And I don't know, if you went exhaustively through all the possibilities, you'll find out that like if I picked 4 things in a three-dimensional cube, that's going to maximize the number of edges. And so what this kind of face is, it's like a subcube of the cube. So generally, a pretty good construction is to take like subcubes of the cube. So take like a copy of, like this is a copy of Q2. This face is a copy of Q2 inside of Q3. Similarly, if I was supposed to pick 2 vertices to maximize the number of edges, okay, obviously I would just pick an edge, which is like a copy of Q1 in Q3. So generally, like I could consider a set of vertices of the form, like I take all sequences where like the first t coordinates can be 0 or 1, and let's say the last coordinate, the last n minus t are all 0. So like, as an example, if n is 4 and like is 2, I would be taking like 0, 0, 0, 0, 0, 1, 0, 0, 1, 0, 0, 0, and 1, 1, 0, 0, right? And this would make like a kind of a copy of a well, in this case, a 2-dimensional cube inside of the 4-dimensional cube, right? Actually, let's back up for a second. Something I probably should have asked is like, can anyone work out how many edges does the n-dimensional cube have? As a function of n. Can anyone work it out? It's kind of a, if you try to extrapolate from the first few examples, it's maybe not easy to see. It goes from like 1 to 4 to 12, and then I think the easiest way to count the number of edges is by handshaking. So what's the degree of every vertex? Yeah, exactly. So, and if I sum the degrees, I'll get n times 2 to the n. But the sum of the degrees is twice the number of edges, so I should divide by 2. So it's going to be n times 2 to the n minus 1, because yeah. Because every vertex has degree n. And there's 2 to the n vertices, and then I divide by 2 because summing the degrees is twice the number of edges. So every vertex has degree n. So by that logic, like since A is making a copy of the t-dimensional cube, then the number of edges in A is going to be t times 2 to the t minus 1. Okay. And what we're going to show is that this is, at least in the case where k is a power of 2, this is going to be the best thing you can do. And then for other values, I mean, of k, we'll get some sort of bound, which will be kind of not an integer, so it'll be a bit awkward. But anyway, so I want to interpret this like t times 2 to the t minus 1 in terms of A itself. So the cardinality of A is 2 to the t, right? So basically, like this is like the cardinality of A over 2. And this is the log of the cardinality of A, the log base 2 of it, right? So t is, so yeah, because A has this size, t is the same as log base 2 of the size of A in this particular example. And then this is the same thing as the size of A over 2. Okay. And what we're going to show is that this kind of bound, this as an upper bound, like this holds for every subset of the hypercube. So of course, like this is going to be an integer when t is when the size of A is a power of 2, but like otherwise it's not really an integer, but still it's some kind of a bound. So you could always take the floor or something, right? So theorem. So for any non-empty set A in the vertex set of the hypercube, the number of edges contained in A is at most log base 2 of A of the cardinality of A times the cardinality of A over 2. Okay. So yeah, and of course this is tight by just taking like a subcube like we did over there, right? Okay. So here's what I'm going to do. We're going to use entropy for this. So pick a uniformly random vertex in A. So just and this makes sense because A is not empty. If you had the empty set, it's like you can't pick anything in it. But yeah, since it's a non-empty set, I can pick a uniformly random element of A and so let's call it X. So X is going to be a sequence X1, X2 up to Xn, where this is basically just the sequence of like coordinates of that random vertex. So each of these things is either 0 or 1, right? Or maybe, like in other words, X really is the random vertex. Or I don't know. I mean, anyway, so, pick a random vertex. It corresponds to a sequence of a binary sequence. X1's the first coordinate, second, up to the nth, right? Okay. So here's the question. What's the entropy of X? And I mean like an exact equality for it. And I guess a hint is there is literally no calculation necessary for this. You can just write it down. Any thoughts? No, it's going to be less than that, I think. So this is like a general principle that is useful in almost all applications of entropy, is this idea that if I take a uniformly random element from some set, like, so basically, like what I guess one question is like, how big is the range of X? The range of X has size A. Like the possible outcomes for X, it could be any vertex in A, right? And I've chosen it uniformly on that range. Okay, yeah. So I've chosen it uniformly from a set of size cardinality of A. So if you choose a uniform random variable, the entropy is just always equal to the log base 2 of the number of possible outcomes. So yeah, probably probably every application of entropy in this course, basically we pick something uniformly, and it's useful because we can just write out its entropy. We can write an exact equality, and then we want to bound the entropy. So we can write this as equal, and then I want to bound this in another way to get some kind of inequality involving that. So if we think about what we want to prove, right? I want to prove that, if you manipulate this expression and solve for the log of A, right? I want to show that log base 2 of A is at least edges of A times 2 over the size of A. If I just divide over, right? And log of A is h of X. So our goal is going to be to prove that h of X, the entropy, is at least 2 times the number of edges of A over the size of A. Because that is equal to that, and then we just move things over and it proves the inequality. Was that clear why that's going to be good? Okay. So now I'm going to do something which is really, it's going to look pretty strange, but h of X, so this is just a number. All I'm doing right now is manipulating numbers. So it's n times, the entropy of X is n times the entropy minus n minus 1 times the entropy. Just because that's how numbers work. The reason I'm introducing this n minus 1 and this n is because I want to apply Hahn's inequality to this thing. So, so just to remind you what that says, it says that the entropy of some random variable x1 up to xn, which is like, that is what x is, like n, like a tuple of n random variables. It's at most 1 over n minus 1 times the sum over all j from 1 to n of the entropy of all of the variables except for xj. So like the entropy of the kind of sequence of variables xi where I is not equal to j. So like this thing is at most that. So if I substitute in here, I'll get there's a minus sign, so the inequality goes the other way. So yeah, I'm going to plug this thing in for this h of x, and then this one stays the same. And yeah, that gives me a lower bound because that was an upper bound here. So h of x is at least n times h of x minus the n minus 1's cancel, so you've got sum of j from 1 to n of the entropy of all of the variables xi where I is not equal to j. Okay, let's kind of bring these together under a common sum. So let's go j equals 1 to n, entropy of x minus entropy of xi such that I is not equal to j. Now, I claim that this is the same thing as the conditional entropy of xj given the variables xi such that I is not equal to j. So I claim this is by the chain rule. Okay. So let me justify that for a second here. So because I'm kind of using it I'm using like a version where I've kind of moved the things around. There's like minuses and stuff, but the chain rule, like for example, so if I take, x1 up to xn, I can say that that's the same thing as, remember, entropy is about like information that you learn, right? By learning the outcomes of these variables. So the number of bits of information I learn by learning the outcome of x1 up to xn is the same as, imagine I first learn all of the variables xi such that I is not equal to j, where j is this some particular value between 1 and n. So like the amount of information I learn is the amount I learn by learning everything except for xj, plus the amount that I learn from xj, given that I already know all of the other values. Okay, so when I go from here to here, all I'm doing is solving for this. So if this minus this should equal this, right? This is what I've got here. H of x is the same as h of x1 up to xn. This is what I've got here. So this minus this should give me this conditional entropy. we go back to our goal, right, I want to show that this thing's at least 2 times the number of edges of A, over the size of A, right? So in the hypercube, like the edges kind of have, each edge has a sort of associated direction. Like if you think of a 3-dimensional cube, an edge could go in like let's say the x direction, the y direction, or the z direction, depending on which coordinate the vertices differ on. So say that an edge UV in Qn has direction j, or is in direction j or something, or the direction of the edge is j, or whatever. So I'll just kind of write uj to mean the jth coordinate of u. So if the jth coordinate is the one where they differ. Okay, so we could break up the counting the number of edges in A, we could break that up by direction. So let's say Ej of A is the number of edges in direction j within the set A. So then, of course, the number of edges in total is just the sum of the number of edges in direction j over all j, right? Okay. So what I'm going to actually do is prove that this conditional entropy for any given j the entropy of xj given xi, like all the variables xi where I is not equal to j, I want to prove that this is at least 2 times the number of edges in direction j in A over the size of A. Actually, it's going to be equal. Let's forget about inequality, actually. This thing's going to be exactly equal. Okay, so if I can do that, then if I sum up over all of this, it'll be equal to the sum of this, which will, on the top, just give me an E of A, like 2 times E of A over size of A, and that'll give me the thing I wanted, right? Because I started with the entropy is at least blah, 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 blah. If I get, the sum of this over all j will just be like number of edges of A over size of A, or times 2. Okay, so I've kind of reduced my goal to this. Is it clear that this is kind of all we need, or? Okay. It's slightly annoying to keep writing this. I think it's pretty clear that the choice of j doesn't really matter, right? So kind of without loss of generality, let's just assume j is n. So let's kind of restate this again. So now that j is equal to n, my goal is to prove that the entropy of xn given x1 up to xn minus 1 is at least 2 times the number of edges in direction n contained in A over the size of A. And yeah, if we can do, in fact, equal. I keep writing inequality. I mean, really the inequality is what we want, but like it's kind of interesting that it's actually equal. Okay. So, all right. This is the only time in this entropy chapter where, like, at some point we will use the actual formula for conditional entropy here, but otherwise you pretty much just you need to know the chain rule. You don't really need to know the formula, but it's going to kind of come up here. Okay, so we think about like an edge in direction n within A. What does that mean? I mean, to contain such an edge, there's got to be some, like if two, you know, for example, right? If we're in 3 dimensions, these two vertices would be in an edge in direction 3, right? So what that corresponds to, it's like you take an n minus 1, a string of length n minus 1, and that string of length n minus 1 contributes 1 to this quantity, the number of edges in direction n, if and only if like both of these are in A. So for a sequence, let's say y in 0, 1 to the n minus 1, we think of like, you know, so y kind of contributes 1 to the number of edges in direction n of A if I guess, I don't know, if I write y comma 0, that just means like put a 0 at the end of y, right? So if that's, you know, this sequence is in A and y comma 1 is in A, and otherwise it contributes 0, right? Okay. And of course, contributing 1 to this edge count is the same thing as kind of contributing a 2 over size of A to the right-hand side of this equation I'm trying to prove, right? So when I say the right-hand side, I mean of, maybe I'll give this a name star. So the right-hand side of star. Okay, so I want to, in some sense, say the same thing about the left side, that some sequence contributes 2 over A to the left side, if and only if it has this property, and otherwise it contributes nothing. Okay, but what does it even mean for, how does a sequence contribute to this side? So for this, maybe we need to, maybe write down formula for conditional entropy. Yeah.
Could you just re-explain the contributing to over the size of it to the right-hand side?
Yeah, because so basically, like for every y that has this property, it makes this go up by 1. If that goes up by 1, like there's a 1 and then like 2 over a in there. Yeah. Yeah, so this we can write as the sum overall y in 0, 1 to the n minus 1. Probability, so this I'm just using the actual formula for conditional entropy. So the probability that x1 up to xn minus 1 equals y times the entropy of xn given that x1 up to xn minus 1 is equal to y. Okay. So now I want to think about how much does each y contribute to this, right? If it contributes the same amount to the left-hand side as the right-hand side, then these things are equal, right? So the thing is, if I've got a y, so like there's kind of 3 cases. Like take a sequence y of length n minus 1. Either, so if I add a 0 to the end or a 1 to the end, either neither of them are in A, or one of them is in A and the other isn't, or they both are. Like it could be this one in and that one not, or this one in or that. So there's kind of 4 cases, but two, the one or the other one is kind of the same. So if neither of them are in A, then there's actually, so for a given, so for some y in 0, 1 to the n minus 1, so if y0 is not in A and y1 is not in A, well, then the contribution's 0 because there's no chance that x1 up to xn minus 1 could be y. So the contribution is going to be 0, right? This requires kind of thinking about, I mean, what was the original distribution? What I did was I picked a random vertex of A, and then x1 up to xn was that sequence, right? But the only way that the first n minus 1 coordinates could equal y is if the thing I chose was either y comma 0 or y comma 1. But if it couldn't have been either of them, then this sequence cannot equal y. So yeah, in this case, the contribution is 0. Now let's think about what if y comma 0 is in A and y comma 1 isn't. So in this case, this probability is not 0 anymore. In fact, it's going to be like 1 over A, right? Because the only way that the first n minus 1 coordinates could be y is if my original choice was y0. So there's one chance of that, and every possibility had probability 1 over size of A, right? It's a uniformly random choice. But I claim that this is going to be 0. So I know like this whole entropy thing is still new to you guys, but if you think about maybe think of, if you think about it in terms of information revealed or something, I mean, why would the entropy of xn, given that we know that the first n minus 1 coordinates give you y, why would that have 0 entropy? Yeah, exactly, right? Because, I mean, if I know that y comma 0 is in A and this one isn't in A, if I know that the first n minus 1 coordinates give me y, there is no choice for the last coordinate. It is a 0. So knowing this information immediately determines the last coordinate, because this one's in there and that one's not. So revealing the last coordinate after revealing the first n minus 1 gives no additional information. So indeed, this is going to have entropy 0. And you can kind of, if you want like a formula that tells you that, I mean, think about what is the range of this. Oh, sorry, this should be equals y. Right? If I fix that this is equal to y, then xn is a variable with a range of size 1. And so, yeah, the entropy is log base 2 of 1, which is 0. So in this case, it also contributes 0 to the sum. And the same thing if I was to switch it around and say y comma 0 is not in A and y1 is in A. It'd be the same thing. So like all of these, any of these cases don't contribute anything. So the only thing that can contribute anything is when both of these things are in A. So now let's think about if y comma 0 is in A and y1 is in A. Then the probability that x1 up to xn minus 1 is equal to y. Can anyone see what it's going to be? So I pick something randomly from A, and I want to know what's the probability that the first n minus 1 coordinate. So given this, what's the probability of the first n minus 1 coordinates give me y? Yeah, exactly, right? There's two chances. It could be this one, it could be this one. And yeah, everything has probability 1 over A, right? And now this conditional entropy we can kind of reason this out, what that must be. Any thoughts though? So do you get that by reverse engineering like what it needs to be? I mean, because I did say that it has to contribute 2 over A, right? Or did you get it by another way? Like, so can you see a way to get that from properties of entropy?
Just revealing the last bit, and it's got 2 possibilities.
Yeah.
It's just one bit of info.
Totally, yeah. Yeah, and you've got 2 possibilities. It could be, once I know that this is a y, and those 2 possibilities are equally likely, right? Choosing this one to begin with is the same probability as choosing that one. So yeah, once I know that the first n minus 1 bits give me y, it's really just a coin flip for the last one. And like a way to say that, I mean, like kind of more generally, this is so maybe I'll write this out with like 2 steps, but that you've got the right answer. That's the right thing. So you could call this like it's the log of the. So because let me just say it's log base 2 of 2, right? You've got 2 choices that are equally likely. The range. Once I know this, the range of this thing is exactly 2. They're both equally likely. So yeah, that's 1. So basically any y in 0, 1 to the n minus 1 contributes 2 over size of a to the left-hand side of star like if both y comma 0 and y comma 1 are in A and 0, it contributes 0 otherwise. So yeah, so so this star thing must hold. Okay, so and then if you go back through the proof, that finishes everything.